Any questions about last class? Okay, let's do a brief recap of where we are. So we have introduced a couple of abstract concepts. First, let me make sure that we are recording. We are recording, that's good. So we introduced a couple of abstract concepts. The first abstract concept that we introduced was the notion of phase space, the idea being that it's a space made up of position and momentum coordinates. This position itself could be R1, R2, R3n for an n particle system, and same thing for momentum, P1, P2, P3n. And in this phase space, if you specify the location, the value of P and R of all 6n numbers, these 6n numbers are what we call a microstate. You have given a most microscopic description of the system that you can think of. Nothing else remains. And so what concepts did we have here? I will label the concepts in red. We have microstates, and together P comma R are points in phase space. Now, notice that I'm talking momentum and not velocity. You could, instead of P, you could have thought of velocity V, which would be P divided by M. It would carry similar information. So those are the two concepts we had. Then we had this concept that if we start the system in one location in phase space and follow what it does as a function of time, it will go through different boxes in phase space. And how big is a box in phase space? Depends on our resolution, or if the finest we can go comes from quantum mechanics, which is uncertainty principle. But we might have our instrument resolution limits. If you're taking a ruler to measure phase space, then probably your unit is going to be 0.1 centimeter or something like that. So it's a measurement question. So but it should be as fine as possible. In classical mechanics, it should essentially be continuous, but quantum mechanics comes and sets a limit. So once we have such a trajectory in blue, which goes through different locations in phase space, we can go and calculate the average of any thermodynamic observable over this trajectory. So let's say at time 1, it was here, time 2, it was here, time 3, it was here, 4 here, 5 here, 6 here, 7 here, so on and so forth, and M over here. So we could go and look at its value at different points, OI, different time observation points I, and average over them. I is equal to 1 to M. And this average is called a time average. So you start the trajectory in one point in phase space and you follow it, what it does as a function of time. In experiments, this is what we really do. We prepare the system and then we let it equilibrate, we let it do whatever it wants to do, and we measure a property. In theory and in simulations, that can be very hard. So that is not the only way to calculate this. And that's where comes the ergodic hypothesis or ergodicity, which says, so this concept of ergodicity, I will color in red because this was yet another concept that we introduced. So these are the things that you should go and look up. These kind of might hide under the rug, but you should go and read up on these concepts because they are really the foundation of this semester. So this ergodicity concept says that forget about following this trajectory as a function of time. Instead of doing that, focus on this mesh of possible phase space points. Okay, you have all possible phase space points. I could keep drawing, but you get the idea. Imagine like a like a chess board or something like that. You have lots of infinite chessboard. You have lots and lots of points. And instead of following the trajectory and seeing where it goes and calculate that observable O in that point, instead go to every box, any such box. Let's go to this box. Calculate the probability that of observing the system in this microstate. P nu is probability of microstate nu, so particular value of R comma P, and then take the value of that observable in this microstate and then sum it over all microstates. This one is an ensemble average. An ergodic hypothesis or ergodicity says the time average is equal to ensemble average. This is almost always going to be true, but I want to give you an example where it won't be true. An example would be, imagine a double well potential. Okay, so you have U of X, double well potential shows up in chemistry. It's one of the first things that you look at, or in physics. And let's say you have a double well that looks something like this. Okay, so if you start your system in this basin, let's color it in blue. It will oscillate around, at some temperature, let's say it's moving around back and forth. Here, I'm not talking about microcanonical ensemble yet. I'm just talking about something quite generic. And at some point, it will go and just move around in this basin, right? So what would be a time average here? A time average of the system would correspond to energy coming from this basin over here and this basin over here. You would get some sort of average energy. So let's say our thermodynamic observable here is X, the position of the system. That's one observable, right? So what would be the time average of X? The time average of X, if you really ran it long enough, would be X1 plus X2 by 2, right? It would go back and forth, and it looks like it's right in the middle on the barrier. That's the time average. What would ensemble average look like? Ensemble average would not involve doing such business of running the simulation or running the system and letting it go from one basin to another basin. In ensemble average, you would prepare half the system in this basin, in this well, and half the system in this well, and forget about time altogether. All of these are approximately X1, all of these are approximately X2, and once again, O, which is X here, ensemble average would be X1 plus X2 by 2, right? Because both basins, both wells I have drawn here are of equal probability. So when you prepare the system, the P nu here, and so I'm stepping a bit ahead, I'm asking you to use your intuition that when you prepare the system, since both wells have the same energy, you should have half the system in X1, half the system in X2. Why is this true? This will really come when we talk about canonical ensemble. So in this case, you can see the time average is equal to ensemble average. Does anyone have a clue? So this is ergodicity is followed. Does anyone have any suggestion for me as to what could I do to this system so it starts to become non-ergodic? Any ideas?
So
when you say non-ergodic, could you elaborate what you mean by non-ergodic?
What do I mean by ergodic?
You just mean that both the spatial average is equivalent to the time average.
I mean the norm of that.
So
so maybe in that case, sort of change the weights that you give to like the X1 and X2.
No, that doesn't matter. You are preparing in equilibrium. So you are asking me to change the P nu. I cannot do that. P nu I am not allowed to change, right? P nu is the probability of microstate. That is given. We are deriving that. We just did it for microcanonical, right? So P nu we cannot control. So that won't work. Sorry. Any other?
So if the potential barrier is high enough so that the
barrier is the answer. Yeah. If you make this barrier higher, what will happen? So you're right, Smithran, we could play with the starting probabilities, but that's really limited. Instead, if you start making this barrier higher,
right,
so high that it looks like this now, infinite, then if you did an ensemble average, you will still have half the system in X1, half the system in X2. But this is kind of similar to what you were saying, Smithran, that now when you if you prepare the system here in this well, it will never go to the right side because the barrier is higher. It will go to the right side if you wait for the age of the universe. It will go because even this infinite barrier means if you wait long enough, you can still cross. But in principle, it won't go there. So if the barrier becomes very, very high, the system starts to look like non-ergodic. So this is, and those of you who like transition state theory can go and calculate how high a barrier should be.
Professor, but
let me finish.
Oh, okay.
Those of you who like transition state theory can calculate how high a barrier should be for it to become non-ergodic. So transition state theory tells you that there is a prefactor nu naught and there is e to the power minus delta G by KT, right? This is the rate of going from one basin to another basin. This thing is around 10 to the power 12 per second approximately. And if you set this rate to be smaller than 1 over, I don't know, what's the age of the universe? It's not 6,000 years that we know, but it's something like a few billion years, right? Let's make it 100 billion years. If you can calculate at room temperature, now you can go and calculate delta G, and you will get a value of delta G, which will tell you how high should the barrier be that you will never get a transition. On the time scale of the universe, the system would become non-ergodic. Such a system can also, the fancy word for it, it is kinetically trapped. So, and you will see that this delta G is not actually that high, 100 kcal or 200 kcal or something even smaller than that, which is the strength of a covalent bond. This is why we say that covalent bonds are irreversible, right? We cannot just break them through thermal fluctuation. While ionic bonds tend to have strength that can break back and forth. Covalent bonds tend to be stronger than, I think this number, and this is a good homework exercise for you for no points, but go and try it, as to what is the value of delta G, which would make this process of going, of course, nu naught is an approximation here, and I'm setting it as KT by H approximately, which is another, we might visit this at the end of the semester. Yeah, so what was, someone had a question?
So I had a question that if we know that the barrier is sufficiently high from the beginning, why would we even consider ensemble in both the both the wells?
This is the heart of the problem. So if the barrier is very, very high, this is why sometimes theory is misused in experiments. In experiments, you might not be measuring something which goes to the other basin. You might be measuring something from only one state. So my message to you here is be careful. If you know the barrier is too high, don't go and assume ergodicity. Okay? Most of the time, ergodicity happens to be true. One of the reasons why it happens to be true is because we are forgetting one thing here, the environment. The environment, now it caused the system to go from one point to another point. But ergodicity on its own is really when m tends to infinity, right? When you observe the system for an infinite amount of time. So ergodicity on its own is true even if the barrier is very high. Mathematically, it just tells you, you got to wait longer. It will happen, right? So it's a mathematical statement. Now, if the barrier is high, like I showed you here, you can calculate this number. Even for a covalent bond, it might start to break, which is something worrying. But we will be working with ergodicity in this semester. Okay, good.
I have another question.
Uh-huh.
Say, what about the case when we have like infinite basins? Say for chaotic systems, will chaotic system necessarily lead to like ergodicity or no?
They are also ergodic. Yeah. Again, if you are willing to wait, m tends to infinity, they are ergodic.
Okay.
And I'm not going to proof of that. This is one of our postulates. This was the first postulate, and as you can see, it can lead to lots of fun and philosophical conversations. We will assume it, and that this time average is equal to ensemble average. And the reason why we can assume this is because we are willing to wait time tends to infinity. It could be chaotic, it could be anything else. Even butterfly effect will disappear if you're willing to really wait infinite time. What is infinite time? That is anyone's guess. In practice, you have to be very careful, especially those of you who do experiments and you have a theorist friend saying, I can do theory for you. You have to be like, are you really sure about assuming ergodicity? Why are you so sure? You should question them. And same for you if you're a theorist. If you're going to apply your theory to some experiments, you should check. Are you sure about ergodicity? These are questions to ask. Okay, so the key hero here is this P nu. Following a trajectory in time is difficult. It's so high dimensional, you cannot do that. But if you could calculate P nu, then you could get the properties of this trajectory by simple averaging, by spatial averaging instead of temporal averaging. And that brought us to the concept of ensemble. And the first ensemble we looked at is microcanonical ensemble, which is an isolated system with constant N, V, and E, total energy E. So for this system, we said that P nu, the probability of observing a microstate is equal to 1 over omega of NVE or 0. It's going to be either constant or 0. When it will be constant? If the, so another symbol I will use a lot is this inverted A, which means for all. Instead of writing for all, I will use the mathematical symbol inverted A. So for all microstate where E nu is in E minus dE to E, and number and volume are consistent with what you have specified, and 0 otherwise. So it's telling us, it's really a boring thing. It's nothing profound here. And this, it's boring, but it has a name. It is called the postulate of equal a priori probabilities. So it means that if you have an isolated system with constant number, constant volume, constant energy, and you can't do any measurement to, you can't couple it with a thermostat, you can't couple with a reservoir of material, you can't do anything, then everything in the system, in this isolated system, must be equally likely as long as it conforms to that energy. And so this was our first example of P nu. And here I emphasized last time that the exact choice of this DE won't matter. And we will look at that today as to why it does not matter. Then the other thing we said last time was that S is equal, normally I won't do this much recap every week, but since we just started and we had a break last time, I thought it's good to get our gears running once again. So, and we showed, we defined our entropy. This is called Boltzmann's entropy. Why this entropy connects with the thermodynamic concept of entropy, we will get to that in a moment. We defined the Boltzmann entropy as this number of microstates log of omega, log of the number of microstates. And we showed that this follows all the nice properties that we expect of an entropy. It is extensive, it is consistent with second law, blah, blah, blah. Okay, we showed all that. And this we called as Boltzmann entropy. This is our connection. So as we go ahead in ensembles, we will always have a partition function. So again, I will color it in red. This one is the microcanonical partition function. Oh, by the way, I wanted to say something. Many of you are international for your visa reasons or something. You might need to have this demonstrated evidence that this is in-person class, which we are not doing. If you have any issues with that and you are on campus, I mean, if you're not on campus, then I don't know how to do in-person class with you. But if you're on campus, we can arrange to meet somewhere outside the campus in a socially distant manner to have a discussion or something like that. If it's bothering you for any reason, okay, we can do something like that if it comes to that. I would rather avoid it. I have no interest in spreading coronavirus for whatever reason or contributing to it. But if you're worried about it, then please let me know. We can arrange that. Okay, so we defined our entropy, our microcanonical partition function, and we said that the log of this is our entropy. And this was wonderful because we could go to our favorite formula from integrated first and second law of thermodynamics. And from that, we could show that 1 over temperature is equal to partial S by partial E at constant NV. Or we define the inverse temperature beta is equal to partial ln omega by partial E at constant NV. I also worked through how you can get all sorts of other thermodynamic properties from this log of omega. So if you can calculate the microcanonical partition function, you have all thermodynamic information inside it. It contains everything. You just have to manipulate it in order to get those things out, but it contains everything. Calculating it is hard. So now we will start, we still have some more material to recap from last time. We are actually going to calculate it and show that Y choice of DE does not matter in this definition of omega and VE over here. So this is what we started doing last time. How did we do this? We said that omega is number of microstates in this phase space, right? It is the volume of phase space that is consistent with what you are trying to do. So what is the volume of phase space? Well, it's a volume integral. It is dx1, dx3n, dp1, dp3n. All of this has to be consistent, and we were doing this for n non-interacting particles in volume V. We cannot do it in general. If you could do it in general, then thermodynamics, statistical mechanics would be even more powerful. We cannot do it in general. As the integral becomes very complicated, all the variables talk to each other. It's extremely hard to integrate. It's basically impossible to integrate if in the general case. In this approximation, we can do it and get intuition for why it does not matter. So this is consistent with this. This integral has to be consistent with n non-interacting particles in volume V. Okay, so it's non-interacting, which means that the Hamiltonian of the system can be written as U as a function of x and kinetic energy as a function of momentum. Furthermore, it's non-interacting, so U as a function of x is going to be 0. There is no potential energy. This means this integral on the left, the space integral, can be done exactly, and that becomes V to the power n, volume to the power n. And then we are left with dp1, dp2, dp3n, consistent with energy in E minus dE to E. This is where we stopped last time. So how do we calculate this momentum part of the integral? In order to calculate the momentum part of the integral, we have to write down the total energy. What is the total energy? Remember, the total energy Hamiltonian is U plus K. We are talking about non-interacting systems. So U is equal to 0. So it's just K. What is K? The kinetic energy is 1 over 2m mass pi squared, momentum squared. I is equal to 1 to 3n. We have n particles. We are thinking of three-dimensional space in which these particles are moving, Cartesian space. So it's this thing. So what we are saying here is that E minus dE should be less than equal to 1 by 2m summation I is equal to 1 to 3n pi square, which itself should be less than equal to E. This is the constraint we need to apply in, I will call this as equation number 1 today, to calculate omega for this integral. Otherwise, this integral would be trivial. How do we do that now? So for this, I will be doing it approximately, but you will get the picture of how it works. So let's consider a circle. Why do we consider a circle? Because if you think about this thing over here, this, as I draw last time, if you're thinking about one particle in 2 dimension, this would have been E minus dE less than equal to P1 square plus P2 square by 2m less than equal to E. That is just a circle. In 2 dimension, it would have looked like 2 concentric circles, and you need to calculate the area between them. So here, what are the axes? The axis is momentum. The axis is all P1, P2. Now, if you go beyond 2 dimension, then you will have P3, P4, all these other axes, right? It's hard to draw 6 dimensions in 2D paper. So this first sphere now, so now we are not thinking of circles, we are thinking of hyperspheres. This first one is a hypersphere of some radius r minus s. The second one is a hypersphere of some radius r. And what we need to do, And what is R here? R is equal to, if we can see from this equation, R is equal to square root of 2em, right? That is the radius of this high dimensional sphere. And R minus S is equal to square root of 2m E minus dE. That's what we have. So our red strip or volume, it looks like a strip in 2D, but in high dimension, it is a volume. It is the volume of that shell that is in between two spheres, a bigger sphere and a slightly smaller sphere, and you want to calculate the volume that is right in the middle. So our red strip or volume will corresponds to the accessible volume in phase space. What do I mean by this? What I mean by this is that any other part, if you were looking at a point here, or if you were looking at a point here, these points are not in accessible parts of phase space. Why? Because either these two in the inside, their energy is below E minus dE. This one on the outside, its energy is higher than E. So they are not allowed. The only allowed points are lying on this strip. So how do we then calculate the volume of this strip, the volume of this little thing? That's why I'm writing it as strip, because volume of volume would sound a bit strange, right? So in order to calculate it, we have to think about what is the volume of, so volume of this strip is bigger hypersphere minus smaller hypersphere, right? The difference between the volumes of these two. What is the volume of the bigger hypersphere? Well, that's going to be some constant multiplied by r to the power 3n. This is where I'm hand waving the math. If you're really fastidious about math, you'll be like, how do you know that? You can see this is true in one dimension. For one particle, the volume would be r cubed, right? If you have two particles, the volume will be r to the power 6. So I'm using sort of a hand waving argument here, but I don't think it's too hard to prove. And the constant, I don't really care about. For one particle, the constant would have been 4 pi by 3. For two particles, it's going to be something else, minus constant multiplied by, and why can we, the thing is we can keep the same constant. Why can we keep the same constant? Because the dimensionality is the same. All we have done is to reduce the volume slightly. R minus S to the power 3n. That's what we need to calculate. Before I get into the math, I want to give you an intuitive picture of what we are going to do next. The intuitive picture comes from the following. Let's say in 2D, you have a circle, right? So the surface area, the area, let's call it the area, not surface area because it becomes confusing. So area by volume in dimension, we have to calculate it in different dimensions, okay? So we will do it in 2 dimensions, we will do it in 3 dimensions. First, let's write down the area. In 2 dimensions, the area is pi r square. The volume is, sorry, in 2 dimensions, the area has to be this thing. So by area, I mean the circumference. So in 2 dimensions, the area is 2 pi r, and the equivalent of volume is pi r square, right? In 3 dimensions, the area is 4 pi r square, and the volume is 4 by 3 pi r cube. So if you take the ratio over here, what do you get? 2 pi r by pi r square, pi cancel, you're left by 2 divided by r. If you go to this one, 4 pi r square by 4 by 3 pi r cube, 4 cancel, and you're left with 3 by r. Notice something happened. For the same radius, the numerator increased. My claim here is that area by volume tends to 1 as dimensionality tends to infinity. That's what we are trying to prove. And even if you get lost in the math of what I did above here, that's okay. But this is something you should try to remember, that you just saw here in 2D, the area divided by area, I mean the circumference. In 2D, the area is the circumference divided by the volume is 2 by r. If you go to 3D, it is 3 by r. You can go and do it for 4 dimension, and you will see it will be actually closer to 4 by r. As you increase the dimension, the numerator catches up, and for the same radius, it becomes close to 1. Radius also increases, but the numerator catches up quicker, and it becomes close to 1. So that's the idea. So what we are really showing here is that in very high dimensions, most of the volume of a sphere lies close to its surface, which is a very bizarre fact. It's not an obvious fact at all. It is something worth meditating over and thinking that it's so strange, but it's true. So we are calculating this. To do this, we are going to calculate this equation. Let's call it equation number 2. So we have some constant in n dimension. The volume will be c r to the power 3n, and we have that's the volume of the outer hypersphere, and then we have the volume of the inner hypersphere, and we have to subtract both from each other. So let's see how to do that. So our volume Vs of this shell over here, all of this, Vs is the volume of this little strip in the middle that we want to calculate. So Vs is going to be c r to the power 3n minus c r minus s to the power 3n. So let's try to calculate it. We can say c r to the power 3n 1 minus s by r to the power 3n, correct? It's exact. I haven't done any jugglery so far, right? It's exact. Now I'm going to do one jugglery. I'm going to say that s by r is much smaller than 1. Okay? So I am saying that if this is true, if 0 less than s by r, and again, what is s? S is dE, and the radius is square root 2em. Okay, so just hold on with me for a moment, and then the math will start to fall in place. If 0 is less than s by r, which is much smaller than 1, then this expression can be approximated. We can write it as c r to the power 3n, and this power that we have over here can be written as 1 minus e to the power minus 3ns by r, right? So at this point, you almost feel like, why aren't you going to contradict yourself then now? Because you're saying that s must be much smaller than 1. Doesn't it mean that dE must be very, very small? We'll get to that in a moment. But if it is small enough, the thing is, we haven't really talked about this part yet. How big can it be? It has to be smaller than 1. So your shell cannot be the whole volume. It can be finite. It doesn't have to be the whole volume. That's what we are getting at. So we have this. This is approximate. So this one was exact. This one is approximate. Now we are going to make one more approximation. We will say that in addition to, so this was our approximation 1. And secondly, we are going to make another approximation that if 3n multiplied by s by r is much more than 1. So we are saying that, okay, s by r is smaller than 1, but let's say the number of particles you have is so many that when you multiply n with s by r, it again goes back and becomes higher than 1. Why is it okay to do that? In statistical mechanics, whenever someone asks you a question and you get stuck, with a very high probability, you might be able to escape the question by just saying thermodynamic limit. If you, it won't always work, but it'll work many times. This is thermodynamic limit, right? We are interested in n tends to infinity. For a very, very large n, this is probably going to be true. If this is true, then e to the power minus 3n s by r equal to e to the power minus infinity equal to 0, right? I have a chat message. Okay, someone texted me about someone being out. That's fine. That's why we're recording the videos. So what does this mean? Suddenly we have shown that this means that Vs is approximately the volume of the bigger thing. That's really strange what we just proved, right? If n is tending to infinity and S by R is much smaller than 1, then the volume of this shell is not going to be very different from the volume of this whole big hypersphere in yellow. That's what we showed. The crucial thing for this to happen is that n tends to infinity. In other words, what we have just shown, that for any reasonably thin shell, the volume of the shell is same as volume of the sphere, of the hypersphere in high dimensions, which are valid under thermodynamic limit. And that's wonderful. This means that whether you have DE or 2DE or 3DE or even 100DE, it's not going to matter. Instead, if you have n multiplied by DE, then it could start to matter, because then this approximation will start to break down. So this is why in microcanonical ensemble, it doesn't matter how precisely you specify your energy. You can take your energy, your resolution can vary, it's not going to make much of a difference. So this is an important ground for building up our study of StatMech, this fact that the precise choice of, that's why we can just write omega NVE. We do not have to go around specifying the value of DE for doing it. Omega NVE is independent of DE. Is this clear? This is a bit funky math. It's probably funkier than the math we will see in the remaining few classes. The math will build up. The math is the language in which we talk StatMech, but it's a bit funky. If you go and Google on this, you will find even more rigorous proofs. And if you want, you can go and look it up. You will see, you can calculate the constant. You can actually go and calculate the volume of the hypersphere in n dimension and show it all happens. I gave you a cheap chemical physics or hand-waving argument for why this is true. Any questions?
Yeah, I have a question.
Right.
Like, I don't exactly understand how 1 minus del r by 3n is written as e to the power minus 3 n del r by r.
Which one?
I don't.
Here?
From exact to approximation. The step from exact to approximation.
So which line? Line number 1, 2, 3, 4, 5, 6. Which line?
Okay, when we are going from the exact step to the approximation step, and we're writing in terms of
Tell me the line
exponential.
number. 2 to 3, roughly? 2 to 4?
Yeah, 3. Yeah, 2 to 3.
Oh, do you remember the series for e to the power minus x? E to the power x?
Yeah, 1 plus x plus n x squared by 2 to 1.
That's what we used here, and ignore all of this. So e to the power, I know it confused me also the first time. E to the power minus 3ns by r, if x is small enough, that is 1 minus
1 minus 3 and
yeah,
minus 3 n by r.
yeah. That's what we used. And then think about taking a log of the whole thing.
Okay, okay.
Okay, it's a bit confusing. If it still confuses you after the class, ping me on Slack, okay? And I will write down a full proof. Okay,
Got it.
great. So why did we do all this mathematical jugglery for a system which in practice is going to be impossible to create? How would you create a microcanonical ensemble with constant energy? It's like saying something exists, but I cannot study it, right? It's the universe. If you really want to be careful, the only microcanonical ensemble is the universe, which is isolated from everything else. If we assume that there is nothing outside the universe, that's a microcanonical ensemble. But in practice, NVE ensemble is hard to create. I know there are many experimentalists in the classroom. So I just want you to think about it. In simulations, students like Shams or Nathan or myself can create it. We can do whatever you want. We can create anything. In simulations, it's all garbage, so who cares? But in real science and experiments, how do you create a constant energy system? It's really, really hard. You might have to make some sort of furnace. Maybe you could do something funky. It's not impossible, but it's just very, very hard. In practice, what is more common is a constant temperature ensemble, constant number. So you create a beaker. Let's say you have a beaker, and in beaker you have put a certain number of things. You put a piston over here and you clamp it down and you force it so it doesn't move. So the number is constant. The volume is now constant. And you put it in contact with the atmosphere. If you do that, it is a constant number, volume, temperature system, right? Because now the atmosphere is at temperature T, and if you're allowing heat to exchange between both of them, which is typically what will happen, right? You will have to design a perfect thermally insulated system for this to happen. And you might be able to do that. You might be able to design a perfect thermally insulated system where heat exchange is not happening. The problem though is, what will you do with this system, right? You cannot go and check anything. Anytime you go and put your thermometer inside that or do any experiment on it, anytime you shine some light on it, you're changing the system, right? So NVE is very hard to design. Meenal looks unhappy. Meenal thinks NVE is easy. Is that so, Meenal? No? Any confusion? If there is any confusion, you guys please stop me. And sometimes I might sound like, why are you stopping me? Let me continue. But that's not my true sentiment. My true sentiment is, it is wonderful that you're stopping me. Because most of the professors, they just complain that Zoom is like speaking to a bunch of gray or black boxes. So when you stop me, it's wonderful because I know that you're there. So if there is any confusion, please stop me, okay? I might tell you, hold on for a moment, let me finish this chain of thought, but I will come back to it. So in practice, it is easy to create an ensemble which is at fixed number, volume, and temperature. Such an ensemble is called a canonical ensemble. Just like the microcanonical ensemble was called NVE ensemble, often this is also called as the NVT ensemble. So the question is, now we have, and so how do I define this? A canonical ensemble, and again, this is a new concept. I'll try to color the new concepts in red. A canonical ensemble can be defined as an assembly of all microstates consistent with fixed N and volume V. Okay? Energy can fluctuate. So we are no longer saying that the energy of the microstate, the potential energy plus kinetic energy, must be E. We allow it to fluctuate. However, well, that's a terrible however. The system is kept in thermal equilibrium, not mechanical equilibrium. If we had mechanical equilibrium, then instead of NVT, we would have to talk about NPT, pressure. So we are kept in thermal equilibrium by being in contact with a heat bath at temperature T. So this is our definition of a canonical ensemble. And the question now is, what is the probability of a given microstate? if a given because we are now allowing the energy to fluctuate, right? So let's draw how will this look like. So we can imagine that, let's say this is one copy of the system. And for this ensemble, the notion, those of you who are like this ergodicity, like Kishla was saying, this ergodicity seems like a pretty weak thing to me. Most of the time, the barrier is going to be very high. Why do you even assume it? Yes, it might break down. However, when you do assume it, it can be very powerful. For macrocanonical, it didn't seem that way. For canonical, you will start to see the power. And why did we do all this macrocanonical mathematical business? Because we will derive the canonical ensemble from this equal a priori probabilities. That's our starting point for deriving canonical. So those of you who, many chemistry students like to read, or even physics background students like to read StatMech from Macquarie's book or one of the other books. Macquarie does not derive canonical ensemble the way I am going to do. This is really the Chandler way, which I like a lot. I think it's more intuitive. I will talk about the Macquarie way later. It's a maximum entropy formulation. This is a Taylor series based formulation. So whoever said Taylor series in the first lecture as their favorite math equation or thing should become very happy now. So what we are doing is to create a microstate of a system with number n and volume v and some energy E1. We don't know what E1 is because we haven't been told what E1 is. We have been told its temperature should be T. So we could create another copy of the system with energy E2, number and volume V. We could in fact create many copies of the system. Let's say there is the newth copy of the system with energy E new and number n and volume V. We could create such infinitely many copies of the system. So the question is, how many copies would have energy equal to E new? That's the question we are trying to answer. The answer I will give you in advance. You have all seen it in PChem, but if you haven't taken StatMech, you probably haven't derived it or derived it in an ad hoc manner. The answer is that P nu is proportional to e to the power minus beta E nu, where beta is equal to 1 over Boltzmann constant multiplied by temperature. This is the probability for a canonical ensemble. And that's what we are going to derive in today's class and next class. How do we do that? How do we proceed with this? So in order to do this, so each of this is a microstate of the system. This is microstate with energy, microstate 1 with energy E1, number V, number n, volume V. This is microstate nu with energy E nu, number n, volume V. Sometimes my nu might look similar to V. I apologize in advance. Nu will typically have a bigger flare to the right. So in order to calculate this E nu, we take into account that we have also been told that the system is in contact with a heat bath at temperature T. So let's draw a big heat bath over here, big one. Okay, this is our heat bath. And let's say each of these can exchange energy with our heat bath. However, the heat bath is so big and it's so massive, it's pretty much like the whole universe. We assume that the heat bath itself is thermally insulated. So I am drawing this dashed line over here. Typically, this dashed line means thermal insulation. So we have done something interesting here. So a good idea might be to write this heat bath inside before we get confusing. So this is our heat bath. And this now is our system. Copy 2. This is system copy nu. So we have different copies of the system in thermal contact, in thermal equilibrium with a big heat bath. And the key point here is that heat bath plus system together is thermally isolated. And pressure also, it's just isolated. It's an isolated system. Let me just call it isolated to keep things simple. It's an isolated system. What does this mean? This means that energy of the bath plus energy of the system in any state nu must be equal to some constant E, right? We are saying that E nu can fluctuate. It can be value E1, it can be value E2. If E nu is E1, then E bath must be E minus E1. If E nu is E2, E bath must be E minus E2. Their sum cannot change from some constant value E, because we have designed our system this way. This is a mathematical construct in order to understand, or physical construct, whatever you want to call it, in order to understand what it goes on. So together, the heat bath, and the system can be treated as a microcanonical ensemble. That's the key idea. Together, bath plus system can be treated like a microcanonical ensemble. This will be our starting point to do all of this, with one further assumption that always E bath is much more than E nu. Bath is much bigger than system. That makes sense, right? You have a tiny system and you're embedding it into a reservoir, which is enforcing the temperature. The reservoir, the bath, is way bigger than the system. So E bath is much bigger than E nu. That's one assumption we have over here. So now let's calculate the total number of states accessible to this system, because now we are going to treat total number of states accessible to this system plus bath. Why do we do that? So we will focus on system plus bath, because they together are a NVE ensemble. They are a microcanonical ensemble. And count total number of states system plus bath can take. So let's try to calculate this. So and this is now a counting business. StatMech is really counting business. All you do is to count all the time. So if the system is in some state nu, that is, and let's say the energy of the state nu is equal to E1, then what can we say about the number of ways the bath can be arranged? Since we have, this is a subtle point, Chandler goes through this argument. So if this is confusing, go through Chandler, but trust me, Chandler goes through it quickly. So it's best to pay attention right now, which is good in general. If you have specified the energy of the system to one value, E1, then the bath itself is now microcanonical, right? Because you have fixed the value of the energy of the system, right? So this is subtle, but it's important. So now you can calculate omega, and I will put a bath because I'm treating the bath as a microcanonical system of E minus E1. This is the number of microstates the bath can take, right? If the energy is equal to E2, the number of microstates the bath can take is E minus E2. Dot, 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 if the energy is equal to E nu, the number of microstates the bath can take is E minus E nu. When I came to grad school in the United States in 2007, my StatMech class would be taught after lunch at 1 p.m. And this is the point around when I would fall asleep in the class. And it would be terrible. So please don't fall asleep. This is important, and it's a good thing it's not happening after lunch. So,
I have a question.
Yeah, go ahead.
The number of ways the bath can be arranged. The bath means that is excluding the system.
Yeah.
So we are calculating the number of microstates for both the system plus bath, and Okay.
So far
These-
over here, I have talked about number of ways the bath can be arranged, right? I haven't, what you're picking at, I think, is that I have not talked about number of ways the system can be arranged,
Yeah.
right? So what?
Yeah. And the energy E1 is for the energy of the whole system plus bath.
No,
E1,
energy is
or
for
it-
the state of system. So I should clarify this here. This is the system. If the system has an energy E1, the number of ways the bath can be arranged is omega B E minus E1. Okay? So actually, let me do one thing and add another column over here. Number of ways bath can be arranged. You also have to think about number of ways system can be arranged. And the way Chandler works with this is he puts everything as one. It's not one, it's a small number, okay? It's a small number. The number of ways the system can be arranged is always going to be smaller than the number of ways the bath can be arranged. Remember why? Because in the last class, we talked about how omega as a function of E explodes, right? So the bath is somewhere here. The system is somewhere here. This is the system and this is the bath. The number of ways the bath can be arranged is way more than the number of ways the system can be arranged. So much larger that instead of fixating over what is the smaller number, just set it to be equal to 1 and don't worry about it. The derivation as follows, you will see that how even if you set it to some other smaller number, it would disappear, it won't matter. But for now, let's just set it equal to 1. So now if I ask you, what is the probability of observing, here comes the nice part, the system in state nu. We can now write it down. That will be the number of possible ways you can arrange, number of ways system in E nu, comma, bath in E minus E nu, divided by total number of ways. That's probability, right? This is subtle but simple. So we have just calculated the number of ways the system can be in E1, number of ways system can be in E2, number of ways system can be in E3. And if I ask, if these were the only 3 possibilities, and let's say this number was 5, this number was 10, and this number was also 5. And now I ask you, what is the probability of observing the system in the first state, 1, then the answer would be 5 divided by 5 plus 10 plus 5, right? You just don't have 3 of them, you have many, many, many of them, but it's going to be proportional to this thing. And this thing is just a proportionality constant. The denominator is just a proportionality constant. So we can say that the probability of observing a given microstate is therefore proportional to omega bath of E minus E nu. We haven't yet derived Boltzmann's formula, but we are getting there. It is still far from Boltzmann's formula. Okay, how do we proceed here now? So one trick we are going to do now is to, instead of looking at omega, because it is such a huge number, it blows up. So right now we wrote that T nu is proportional to omega bath E minus E nu. This is exactly the same as exp of log of omega b of E minus E nu, right? I haven't done anything. I have just said e to the power log is 1. It's the same thing. And why have I done this? Because this is more tractable. This is more tractable. It's a nicer number. Log of omega is a nicer number. Log of omega represents entropy, right? We know that. It is related to the entropy. So it's a thermodynamic thing. E to the power entropy, however, is going to be a huge, huge, huge number. So we know that our P nu is going to be proportional to this. Now comes in our Taylor expansion, because we just said that, let's number a few more equations. So when you go back, you can refer to them where we had numbered equation 2, and then let's call this as equation 3. Let's call this as equation 4. So we have equation 3 tells us that E nu is much smaller than E, right? And that's where we can now start to use our Taylor's expansion. Therefore, ln omega E minus E nu is going to be ln, we do a Taylor expansion around E. So this is going to be ln omega bath at E minus E nu multiplied by partial derivative of log of omega bath by E, partial derivative with respect to E at constant NV plus higher order terms, which we are going to ignore. Because E nu is much smaller than E. So we can do that. Therefore, ln omega BE minus E nu is approximately ln omega B of E minus E nu. What can we say about this thing? This looks very funky, but anyone has intuition for what this might be? You can just unmute and say, or chat, or put it in chat.
It was
Somehow related to
pressure, right?
temperature.
Go ahead, Shams.
Somehow related to temperature.
Oh, well, be more precise. You're a scientist. How? And which temperature?
Because del S by del E equals either 1 by T or T. I don't.
Comes out to be beta.
Omega is related to entropy, right?
Yeah, so it is, yeah, so you can be precise. This is nothing but beta bath. Right? This is beta bath. This is the inverse temperature of the bath. However, something interesting can be done now. Beta bath is the same as beta system. Why? Thermal equilibrium, right? There is no two different betas. We are talking about thermal equilibrium is equal to 1 beta. There is 1 beta for the system. Therefore, ln omega B E minus E nu. This derivation looks complicated, but I love it because it's so simple and it's one of those things that I can derive without looking at a book at all. I haven't looked really at my notes for this because it's unlike the Macquarie way where you will get confused. The Chandler way is so intuitive, you can do it, you will never forget it once you understand it. Minus beta E nu. Let's call this as equation number 5. Use 4 with 5. P nu. So this is ln of omega b, right? So we have ln of P nu is therefore proportional to ln of omega b E minus beta E nu, right? Therefore, P nu is proportional to e to the power ln omega BE multiplied by e to the power minus beta E nu. This is a constant. There is no nu over here. This is the total energy of the system plus bath. This has nothing to do with the microstate, right? This is microstate independent constant. Therefore, P nu is proportional to e to the power minus eta B nu. And we have just derived the probability for the canonical ensemble. And what do we, so we have just showed that P nu is proportional to e to the power minus eta B nu. The argument here was Taylor's, that the system plus bath is a thermally insulated system. And number 2, the system is much smaller than the bath. So we could do this. Then this one has no nu in it. There is no nu over here. So it's just a constant. So P nu is proportional to e to the power minus beta E nu. And we call this as equation number 6. What do we expect of a probability we expect a probability to be more than 0. Well, that's clearly true because it's an exponential. We expect a probability to sum up to 1. We expect that p nu over all nu must be equal to 1, right? So in order to do this, we define p nu is equal to 1 by q e to the power minus beta e nu, where q is equal to summation nu e to the power minus beta e nu. So the full definition of p nu is e to the power minus beta e nu divided by summation all microstates e to the power minus beta e nu. That's the canonical probability, canonical ensemble probability density. And this q is now a function of beta, number, and volume. In fact, let's write it as a function of number, volume, and beta. And it is given by summing over all microstates e to the power minus beta e nu. This is our canonical partition function. This is the second partition function we have seen so far in the course. Last time we saw microcanonical partition function. This is the canonical partition function. It contains exactly as much information as the microcanonical partition function. In fact, you can show that this is a Laplace transform of the microcanonical partition function. So there is no new information here. It's just a different way of looking at it, depending on whether your system has constant temperature or constant energy. And some books also use the symbol Z for it. They call it as ZNV beta. I will be using this in some books. I will be using Q for this because I'm going to use Z later for something else. Most importantly, you should always specify the variables. It is like a code. It is like a function in a computer code. It's good to specify what function you're calling, but best is to specify what are the parameters for this function. And if you think that God is a programmer, you can really think partition function is something like that. You have to specify what are the parameters, what are the variables that this function needs to have in order to be called. So never write Q, always specify Q of NV beta. Of course, equivalently, you could have written Q of NVT. There is no difference over there. So you can call it an NVT ensemble or an NV beta ensemble. The reason why this is nicer is because we can write down P nu as proportional to e to the power minus beta e nu. If we were using Boltzmann, if you were using temperature, then it would be P nu is proportional to e to the power minus e nu by kBT, which is just a bit more to write, right? So beta just takes care of the Boltzmann constant. And this is wonderful now, because now if you want to calculate thermodynamic observable of anything, and I'm going to stop here now, I want you to go and try to do it on your own before you look up the answer from a book. Next time, we are going to see that the average energy of the system is given by minus partial of log of Q by partial beta at constant NV. I want you to try to prove this. We will work through it carefully. We are not going to rush through it, but I want you to try proving this on your own. If you look it up on the internet or in a book, it's everywhere. The moment you look it up, the fun is gone. So try to do it completely on the basis of what I have told you so far. And your hint is that E bar is equal to summation P nu E nu. And you have P nu over here. So this is summation 1 by Q e to the power minus beta e nu multiplied by e nu. And I want you to calculate it and show that this is the same as this thing. Once you do that, the next class will become very easy. So it's worth it. Next class, we will look at other connections for Q, this partition function and thermodynamics. And we will move on. We will look at how, we will see how the canonical partition function is really the same as microcanonical, and the thermodynamic limit, they don't carry different information. It's just a question of how your experiment has been set up. We will also look at the heat capacity. So in the very beginning of the semester, I told you that the heat capacity is related to the fluctuation in energy, and that statement will make a whole lot of sense. And we will see why in thermodynamic limit, fluctuations disappear. So next class, we will start talking about fluctuations, which will be, fluctuations are really the heart of StatMech. And then what we will do is to look at some examples using microcanonical ensemble and canonical ensemble, use these formulae to calculate thermodynamic properties and show that the ensembles really give you the same answer. However, the amount of work you have to do might be different. So often you have to decide which ensemble is going to help you more for a given problem. And that's when you proceed. And I'm going to release the graded answer sheets before releasing the next homework, but you will have it you'll probably have the next homework a week from now with another week to return it, which will have a lot of problems using microcanonical and canonical ensemble. Okay, any questions?
I have a quick question. Like on the previous page. Yeah, the first line is P mu is proportional to the number of microstates of the heat bath, but does the like introduction of exponential and ln goes away with like we don't have to introduce a proportionality constant?
No, that is exact, right? Because e to the power log of a is equal to a.
Yeah, but in the previous expression, it was like a proportionality constant.
Oh, no, this is, okay, I see what you mean. This is still proportional. I meant these two are the identical thing.
Yeah.
P nu is
So
still.
don't we have to introduce a proportionality constant somewhere?
We
like,
could, but we just disappear. We had one over here also, right? So you could call it some proportionality constant K. It won't matter because it will again disappear over here. You can try to do it. You can be precise about all proportionality constants, but just like this proportionality constant at the very end disappeared, it doesn't matter. What we have tried to derive here is P nu proportional to e to the power minus beta nu, right? We ignored the value of the proportionality constant completely. We might be able to do that, but it doesn't help. The way we define the proportionality constant is then by saying that it is the sum of e to the power minus beta e nu over all microstates. And then we give this proportionality constant the name canonical partition function. Okay? So you could keep it, it will just disappear in the end. Any more questions?
Can you go to the page 1?
Page 1, all right.
Yeah. My question is that for the first that you have many microstate. So when we derive off this, do we need to make sure that the number of the microstates they are finite, or the microstate they are just infinite numbers?
So that's a good question. I will have to think about it. So
I have a
the
question related to that, but
so the number of microstates in a microcanonical ensemble cannot be infinite, because if it was infinite, the entropy would blow up. Okay?
Oh yeah.
So anytime you specify an energy, you are saying that the number of microstates must be finite. So that's how I solve that problem. It's not the best solution, but that's my intuitive understanding. Okay?
Okay. So it's like I'm sorry. So it's like that we have something that to constrain to let the microstate finite. It can be energy, temperature, or some of the constant we give in the ensemble, right?
Yeah. So if you allowed all energies, then the number of microstates would be the area under this curve that I drew over here. This will clearly blow up very soon, right?
Yeah.
If you were to count number of microstates with all possible energies, sure, it will go to infinity very quickly. That's why we kind of started to deal with log of number of microstates. But for a given energy, the number of microstates must be constant because we know entropy is finite. Okay, good. Any more questions? All right, so Thursday I will also have office hour, otherwise, and I will see you in 2 days from now. And we will work on canonical ensemble. And what I want you to do is to think about this formula at the very end of page 8 and try to derive it. Be very honest with yourself. There is no points for this. Try to do it just on the basis of this note. That's it, and see if you can derive it. It will be very good practice for you. Okay, so see you all next lesson.